Hi again. So, if we look at these slides again, the idea of a banker's algorithm is basically to avoid deadlock altogether, right? So, it's more like a deadlock avoidance kind of thing, right? So, since we know how much each process needs, and we know how much a process needs in maximum amount of resources, and how much is currently available, right? And how much is currently allocated, we can kind of choose the processes that how the processes can run such that a deadlock does not occur, right? And we make sure that this does not occur by assuring that there's always enough resources for things to run, right? Okay, so in this case, let's consider we allow P1 to run, right? And P1 requests more resources, right? The resource that it requires is A, 1 of A, 0 of B, and 2 of C, right? And if we consider this, we can see that now P0, the resources reduce, right? Previously we have 332, right? Now if we give it one more to P1, then P1 will get one more resources, right? And so now 3 minus 1 results in 2, right? 2 resources available, right? And this remains 3, and 2 has been allocated, so C becomes 0, right? So the ones available now is 2, 3, 0, right? And you can see now is that P1, because it gets 102, you can see the amount of allocated to it actually increases, right? Now, and how much more it needs basically reduces, right? So previously it amount allocated is 200, and the maximum is 322, right? Now it gets the resources, now it becomes 020, right? And if you look at P1 now, if you look at, if this request is granted, right? P1 is asking for 102 and it's granted. Now the available will become 230, right? Now if you look at the resources that currently each process needs, now which one does it satisfy for it to move forward, right? So none of these processes can move forward, right? Except for P1, right? Because now P1 requires 020, and the ones that are available is 230. It still will be able to get this process B, right, in order to run, right? So if you try to follow this algorithm, then you would give P1 the resources, right? If you give P1 another 2, right, it will get to finish. So once it's finished, it doesn't need anymore, and it will release the allocation. And once it releases the allocation, all of these resources becomes available again, right, available again. So now if you give 2, now it'll become 322 for P1, right, allocated. And if it gets all the resources, because the maximum amount that it needs is 322, right? So when it gets all the resources, it will release 322, and this amount of available will again be available, so it will become 5 sorry, it becomes 552 in this case, right? Then it will be able to satisfy other processes. 552 would allow P3 now to run, right? And then P3 resources allocation again, then it will have P4 run, right? Then P4 would release allocation again, then it would release P0, right? And finally it will request for P2, right, in order to finish it safely, right? So, but at the time where T0 move from, T0 move where P1 requests, you can see other processes basically cannot make any request to be and be granted to use the resource, right? Now, this is a banker's algorithm with the safety algorithm. Basically allows you to avoid deadlock altogether. But what if would not actually, what if we allow it to run without actually avoiding things, right? So if we do have that, then we have to detect when we are actually in a deadlock, right? And if a deadlock actually occurs, right, then how do we recover from such cases, right? So the operating system kind of do this, right? Either we decide first before we run whether we end up in a deadlock situation, right, and choose processes to run in such a way that we avoid deadlock altogether, or in the case we let it run, and if a deadlock occurs and we detect a deadlock, how do we recover from this deadlock, right? So in order to detect that there's a deadlock, we need some kind of a deadlock detection algorithm, right? And this is one of the idea is to use a resource allocation graph, right? Right. So process I is pointing to Pj, right? If Pi is waiting for Pj for something, right? And let's look at this algorithm per se, right? So we have process T1, T2, T3, and T4, right? This is the resource allocation graph, and we can actually come up with the wait for graph. So we can see T1 is somehow requesting for R1, but R1 is actually held by T2, right? So if we look at this, we can see that T1 is actually waiting for T2, right? And the same thing for here, we have a resource allocation graph. T2 request for R3 and R4, right, and R5, right? But things are being held by T5, T3, and T4, right? So we can see that T2 is actually waiting for T5. There you go. T5, T3, and T4 in this case that are holding those resources. So you can basically draw this graph and basically identify if there is a circular wait happening, right? And whenever we have a circular wait here, then obviously we have a problem, for example in this case or in this case, right? So where a deadlock will occur, right? And if a deadlock occurs, then we have to do something to break from this circular wait, right? Okay, so let's look at this again, on how to have a detection algorithm besides the resource allocation graph, right? Here we define a vector, what's available, and the work that needed to be done, right, and whether the work is finished or not, right? So so in this case, if we have enough resources, we can do the work and we finish, right? If we don't have enough resources, then we still continue on requesting for it. And if most processes are not finished, then we detect a deadlock, right? In this case, right? So if finish, right, for all I until to n, the system is deadlocked. Basically, if most processes cannot finish, then it is considered a deadlock, right? Now let's look at the example for this, for a detection algorithm, right? There are 5 processes here, P0 through P4, right? There are 3 resource type, again 7, 2, 6, a bit different, right? And you know, A have 7, B have 2, C have 6, and currently what's allocated at T0 is given, right? The current request being made by each processes, right? And what is available, right? So if we look at this one, you know, what will allow any process to run, right? You know, this process P0 request for 000, request for none, right? And P2 also request for none, which allows basically either P0 or P2 to basically move forward, right? And let's see whether there is a sequence that would result in all the process being finished, right? So you know, so here we can say P0 or P1, sorry, P2 here, right? Because you know what's available is 0, and you can't really, you know, allow anybody to request anything more. So the only ones that we can think of that can be allowed to run is P0 and P2, and let's assume that P0 gets to run, right? So if P0 gets to run, P0 would then release the allocation here, right? And now we would have 0, 1, 0, right? We can then allow P2 to run, then we have 3, 1, 3, right? And then here we can allow P3 to 1 to run, right? And then we can allow P1 to run and P4 to run eventually, right? Which would result all in true, right, in running, right? So you can calculate whether you know, whether what is requested actually fulfills the safety criteria, right? So if you find a criteria where you find that you know, you cannot satisfy all of these processes, P0, P1, P2, P3 or P4, then you know you have detected a deadlock, right? Or if you run, right, so you allow here to run P0 to run, P0 will run, and it will release its allocation, so 0, 1, 0, but you can still allow P2 to run and get release this allocation. But if there is a situation where you know the allocation given back is not enough, then basically you would have reached a deadlock, right? Okay, so let's stop for here, and we'll continue back in a bit, right?